First of all, welcome in ESRIN again. I think that our director of ESRIN and of Earth observation made a pretty good introduction of what we do in ESA and here at ESRIN. But our role, mine and of my colleague Mariano since 20 and more years, is working in what we first and usually call the launchers, but now we call space transportation system. We are here to try to explain you why space transportation matters in this context. And this is the objective of this presentation. I hope that they will succeed. So we can go with the first slide indeed. I will just briefly introduce space transportation as managed here at the European Space Agency, and then I will leave the floor to my colleague Mariano to explain you the Vega launcher family. That is indeed our European launcher dedicated to Earth observation satellites, to put in orbit Earth observation satellites. So next slides, please. Why space transportation matters? Of course, you know, and we already talked about it, thanks to a presentation of our director Simonetta, that all what is dealing with climate change, with Earth observation, with the state of our Mother Earth is nowadays really linked to a proper observation from space. Space is a privileged point of observation for what is happening on Earth. But how do we reach space? So satellites, Earth observation satellites, science mission, they cannot reach themselves with their propulsion system, the orbit. So we need a transportation system. Here we are. Space transportation system is the enabling technology, but it's not just an engineering technology, and I will try to explain you what I mean with these words. So it's the enabler to allow to be in orbit and then have this privileged point of observation. So one of the main mandates of ESA since the 70s, since when it was established, was to have an autonomous access to space. At that time, I think that they were very wise in thinking about it, because today is more than strategic to have an autonomous, independent access to space. We have seen a crisis 2-3 years ago with no more access because of lack of European launchers, and we were forced to use US launchers, for example. This is so far worked well because we have a long established cooperation with US, but still it is very strategic and important to have an autonomous access to space. And which is the link between launch system and what is the environmental challenges and changes that are upcoming and are already happening? The link is that thanks to a space transportation system, and we will see, we are also trying to develop technologies that are directly used also for Earth observation, for satellites that are using Earth observation. And so space transportation is the enabler to reach orbit and make possible this kind of understanding of our Mother Earth. So we can go to the next slide, in which you will have an overview. Waiting for the next slide. Yeah, okay. ESA is the ESA space transportation ecosystem. The Directorate of Space Transportation, I was saying to you that first it was called Launcher Directorate. Now it's a space transportation, because we will see and we will witness in the coming years a wider and larger use of low Earth orbit, not just, let me say just entre virgule, for satellites for Earth observation, but we will have for sure a development of a kind of a logistic. You can imagine the first flight of the brothers Wright in 1912. I think that no one at the time was imagining that in 100 years there would have been low-cost companies linking cities all around the world. And what is forecasted for space, that's something not equivalent, but similar will happen in the coming years. We will have a logistic in space with cargo, with refueling, with capability to go in orbit and come back, and with, using the gateway station, for example, as it was planned as a kind of link between Earth and Moon. This will happen, sooner or later will happen. When we can think and imagine something, at the end, finally it will happen, of course, if there is an interest from the commercial or from the societal point of view, but I think it is the case. Which are the space transportation systems that we manage in ESA? Of course, the Vega-C and Vega-E family, but I will not elaborate too much about it because there will be a dedicated presentation for Mariano. But anyway, Vega family is the one that was conceived at the European level exactly to serve Earth observation satellites. This is the core market. Then there are, of course, also other capabilities that Mariano will explain, but this is the core market. Then we have our workhorse. It was Ariane 4, then Ariane 5, and now Ariane 6. It's our heavy launcher. It's intended to put in orbit a constellation of satellites. Yesterday or 2 days ago, there was, 2 days ago, yesterday? 2 days ago, there was the launch of Kuiper satellites from Amazon for internet connection. If you have not seen it, I suggest you to go to YouTube and see the launch, because the launch of Ariane 6 is amazing to be seen with the 4 booster. And it was a commercial mission to put in orbit this constellation of satellites, but also Ariane 5 has been used for a science mission, very important science mission. A large telescope and so on and so forth and so on. And then to increase competitiveness and enlarge the opportunities for potential customer, since last year at the Ministerial, it was decided and approved a program that is called the ELC, European Launcher Challenge, to enlarge competitiveness and increase the capability to reach orbit through launch systems. And this is an endeavor that is taking shape in these months and will probably materialize in the coming years. And with this brief introduction about which is the ESA space transportation ecosystem, I will leave the floor to Mariano to talk specifically about the Vega family of launchers.
Good afternoon. My name is Mariano Genito. I'm the Chief Development Officer in AVIO. AVIO is an Italian company. May you go to the next slide? Oh, okay. AVIO is an Italian company which, as Dante said, has been entrusted beginning of 2000 of the development of the Vega launcher. We have developed and qualified the launcher together with our ESA colleagues, but we also operate the launcher. So we are the launch service provider, is the one that manufacture the parts, assembly, and put the satellite into orbit. Why ESA decided, member states decided early 2000 to build another launcher? Because they had Ariane 5. So the question is why to have another launcher? Because Ariane 5 was designed to carry very heavy satellite in higher orbits. Whereas they recognized that there was a growing interest in Earth observation. And Earth observation is made by smaller satellites, so in the class of 1-2 tons, and in a different orbit. The typical orbit is LEO, what we call LEO, which is low Earth orbit, which is not so far from from the Earth because it's 600, 700 kilometers, in order to allow to put on the satellite different instruments which can measure, as Simonetta explained before, different quantities. And the other peculiarity of this orbit is that with only one instrument on a satellite, you can monitor all the Earth, because in 2 weeks, the satellite will cover the entire world and measuring with the same instruments all the same quantities in all the locations around the world. This means that you can have a continuous flow of data, which allows you to make models, comparison in the years. You have seen the evolution of the ice. This is possible because we have a satellite which is working for us and acquires data all around the world continuously. Member States realized in early 2000 that they were able to design a satellite, operate a satellite, but they do not have a launcher designed to launch this satellite. In fact, these satellites were launched by US or by Russians because they converted the intercontinental ballistic missile to civilian use, but it was scarce. They have few launchers. And so, in order to get independence from these from foreign countries, they decided to design a specific launcher called Vega for the application of Earth observation. The target was to have a launcher with a capability of 1.5 ton in the orbit. We got our first flight, which we call maiden flight, in 2012, and we operated Vega up to 2024, when we had the last flight. During the operation of the Vega, member states realized that they need an evolution of this launcher because Vega was not able to cover all the application in Earth observation. In particular, radar satellites were far beyond the capability of Vega, but also to have the possibility to carry on board several satellites. And this is why was approved Vega-C, which had its maiden flight in 2022, and today is the backbone of the European Earth observation community for launch. During the exploitation of Vega-C, as we did for Vega, we are already thinking about the future. So we have started the development of Vega-E, whose main purpose is to substitute the third and the first stage of Vega-C with an innovative engine which will be powered by LOX methane, which is a green propellant, and so less toxic for the environment. So you can see this as evolution of launcher or a continuous service that we provide to the Earth observation community. Next slide. If you have a look to what we have done so far, we have made 14 years of exploitation, 29 missions, and we have orbited more than 140 satellites. This means that in each mission we carry many satellites, ranging from 1 kilo from students at the university up to the very sophisticated payloads for Earth observation. If we look at the first pie chart, it's clear that Earth observation is our core customer, because 75% of the mission are dedicated to Earth observation. The remaining part, 25%, is always linked to science, but not directly to Earth observation. So mainly we serve institutional needs, we serve the public to allow scientists to get data from space. In the second pie chart, you can see what are the customers which profited of these launches. You can see that half of the launches, half of the mission we have done are for European entities, ESA, European Commission, Copernicus, as mentioned by Simonetta, but also national agencies. So there are several agencies in Europe which develop their own satellites and are launched by Vega. The second half is made by a small fraction which are private customers. So there are some startups or joint venture or either also big companies like Google. We have launched 4 satellites for Google, for example. And there are also non-European national agencies. It means that we serve those countries as we were 25 years ago, which want to enter in the Earth observation, but do not have a capability to access to space. Peru, Vietnam, Turkey, Thailand, there are a lot of countries which contribute to Earth observation, and we enable them to launch their satellite and to get their data back for science. Next slide. So the main evolution was, as I was said, from Vega to Vega-C. A launcher is a powerful machine, something that has to take a satellite and accelerate the satellite up to 8-9 kilometers per second. So it's something which has to be powerful. And Vega was in the class of 100 tons of mass to lift into orbit 1 ton of payload. Vega-C, we have doubled the size of the launcher. As you can see, we have also increased the volume because bigger satellite requires more volume to reach 2.3 tons in LEO orbit. We have also played on the environment because the launch environment is quite harsh, so you can understand that there are a lot of vibration and so on. And so we take careful of the fact that the scientific instruments are sensitive to the mechanical environment, so can be broken during launch. And so we improved what we called the comfort of the satellite in order to allow to embark more sophisticated instruments. One is Eolus, which is over there. This was launched by Vega, for example. The last requirement was precise injection. Why? Because satellites to do their job should be put with a very precise position in space, otherwise instruments cannot make their job. If the launcher is able to put in very precise position, we increase the lifetime of the satellite. Why? Because if the position where the launcher leaves the satellite is not so precise, the satellite should spend some propellant to adjust its position. If the launcher is precise, the satellite can use this propellant to increase its lifetime. We have satellites which were designed for 3 years of operation, which have reached 6 or 7 years thanks to the fact that we have a very precise injection. Furthermore, the last requirement was to increase the versatility of the launcher. So we understood that not all the satellites are big, and we have to enlarge the community which can profit of the launch. With Vega-C, we have the capability, which is quite rare in the world, to place a satellite in 3 different orbits in one mission. And this allows us to embark much more satellites and to offer also a lower cost, because a shared flight obviously is less costly than a single launch. Finally, always on cost, we have developed, taking profit of the fact that we have also the evolution of the Ariane 5 into Ariane 6, of developing one motor which serves as first stage of Vega-C, but also as boosters of Ariane 4, Ariane 6 in 2-on-4 configuration. This allows us to have a certain industrial basis and streamline the cost, but also to increase the reliability, because more production means that you acquire more knowledge and you are able to get higher reliability for the launch. Next. On the side of the accommodation, as I've seen, differently from Vega, Vega-C is able to offer a wide opportunity of accommodation. We have a classical launch, which is made by all the launchers, which is a dedicated launch. This is offered when the payload is at the top of the performance of the launcher, which does not occur frequently, because we have very few satellites of this mass. If the satellite is smaller but even big, we use what we call piggyback accommodation, so we can launch this satellite with several small satellites. The small satellites, in many cases, are not directly operative, but are used for in-orbit testing. The ESA, before investing millions or billions into an instrument, want to understand if this instrument works in space. So we make a small satellite, we launch with Vega-C, and we prove that these instruments can provide the data that we need, for example, or university. There is a lot of, there is a wide policy in ESA for the dissemination. So we want that young engineers understand what is the role of space, what they can do, how they can contribute to the space future. We have a lot of CubeSat made by students, which went in Kourou to assemble in the launcher and to launch their own satellite. We have also another accommodation which we call SSMS, Small Satellite Mission Service, where we cluster payloads of different dimensions, ranging from 200 to 500 kilos. And we are able to offer a service, a shared service. This is, for example, particularly important if you want to launch a constellation, because we have now in these years, we have constellations for the Earth observation with small satellite, but if you have to launch one satellite at a time, the cost of the launch is more than the cost of the satellite. So it's efficient to launch the satellite together. If the two spacecraft have more or less the same dimension, we have a dual configuration, or we can have another shared configuration for constellation, which is the so-called clepsydra. So the message is, we have a launcher. With the Vega, we have acquired the knowledge. We understood that there was an interest, an institutional interest to support the Earth observation. We designed a new launcher, improving the performance of the launcher, but also widening the possibility to other people to enter in this world. Next. Finally, we have been asked to do more launches than we do for Vega and Vega-C. So we have targeted to double the launch cadence from Kourou. We launched from the European spaceport in French Guiana in South America. Today we have, you can see the ZLV, which is the Zone de Lancement Vega, which is the pad where we launched this, our Vega-C launcher. You can see the SRM storage, which is the storage area where we store the pieces of the launcher, and the PCU, which is the location where we take care of the satellite before integrating on the launcher. These three facilities in white allows us to have a certain launch rate. In order to increase the launch rate, due to the dismissal of Ariane 5, we will get the previous building used by Ariane 5 either for the integration, either for the launch, in order to be used for Vega-C and to increase the launch cadence. Next. So, with Vega-C, we have increased the possibility to launch. We have confirmed the strategic autonomy. We are able to support dedicated and ride-share mission. This allows Europe and world to have a continuous Earth observation data streams. You can see here which are the projected launches in the next years, which are fully booked. So we have 3 years of launch already booked. You can see in yellow the ESA mission, and you can also appreciate that these missions are not only single payloads. Most of them are multiple payloads. So we will do our job for the ESA, but we also leave the possibility to other countries or other institutions to access to space. And the last yellow is Space Rider. Space Rider is a new chapter because, as Dante said, we will open a new chapter in the space transportation because the purpose of Space Rider is not to carry a satellite in orbit, is to carry something in orbit and come back to Earth. This is essential because if you think to biology, for example, people which want to make experiments on some fishes, we always speak about fishes, want that fishes come back to Earth to see what's happened in space, to understand if the growth of the plants is different. Can open the possibility to space farm, so production of things in space, thanks to the peculiarity of space. And I think that for this we have a video, or if you want to complement on Space Rider. Thank you.
Coming back on the floor, first of all, apologizing because I forgot to present myself. So my name is Dante GALLI, and I'm the Space Rider Program Manager. I work in European Space Agency since 2007, and I work and since 2003 also in AVIO. We were colleagues with Mariano, so I worked for more than 15 years on Vega, and then I took another endeavor, that is Space Rider. The idea is now to give you a short introduction of what Space Rider is, and which could be the link between such kind of future space transportation and Earth observation and climate changes. So with the next slide, coming. Maybe. Yeah. I was saying, once our directorate was called Launcher Directorate, now it is Space Transportation. We are increasingly going towards what will be a logistic in space. And we are increasingly go from what is a simple, and it's not a simple because rocket science is not simple at all, launch to IOD and IOV. IOD and IOV stands for in-orbit demonstration, in-orbit validation. You have also to take into account, but maybe it's the same in the climate environment, that we use acronyms everywhere. Everywhere we have books of acronyms, and we are also very fascinated in using acronyms. For example, Vega is Vettore Europeo di Generazione Avanzata, very advanced European launcher. Okay, but then every time we have to conceive a name, we exploit our fantasy because we are engineers. We need also some fantasy, maybe. But anyway, which are the objectives of Space Rider? We have to go beyond the launch. So, as Mariano was saying, a system that is able to re-enter from Earth orbit. It is, let me say, a kind of a mini shuttle. You have, I think, all in mind which was the concept and the shape and dimension of a space shuttle. Space Rider has the dimension of basically 2 minivans. We are talking about 9 meters length and is made of 2 modules, so we'll see later in the next slide. And we wanted to address reusability. Reusability is important. It's important why? Because we reduce the impact in terms of sustainability, so we increase the sustainability, we reduce the cost, and we also move forward in terms of capability to exploit technologies that can be effectively reused. It's a reusable robotic laboratory. It's uncrewed, so we have no men on board, and it will stay in orbit around 2 months, at least 2 months. And it will be able to autonomously re-enter on Earth thanks to dedicated algorithms of re-entering and under a parafoil. A parafoil is a steerable parachute. You know the people that jumps from the sky and then are able to exactly land on the precise point. This is our target, but one thing is to do it by human capability to feel, let me say, the wind. One thing is to predict which will be the wind when I will come back with my vehicle coming from 300 or 400 kilometers orbit, and then precisely land on a landing strip. What we will do with Space Rider, we want to do in-orbit experimentation. Microgravity is a very special environment. If you think about all what is commonly happening in Earth in terms of chemical reaction, etc., it is completely different in microgravity. For example, you don't have sedimentation. Crystallization, it happens in completely different ways. So you are able, and this has been already proved thanks to ISS, to the International Space Station, and several experiments that have been done there, that things forms in a different way, are by far more pure, and I mention you an example. There is a US company that has manufactured in microgravity fiber optic. This fiber optic manufactured in orbit has 10,000 times, is 10,000 times faster than current fiber optics manufactured on Earth. Now the upscale, the big leapfrog that we need to do, the big jump that we need to do is how to have profitable and commercially viable in-space manufacturing. Because if you produce 1 kilometer of fiber optic that is 10,000 times faster than commonly used fiber optic, oh, very remarkable result. How can I produce thousands of kilometers of fiber optics in space? This will be the next step. We can do materials and science in microgravity, and the most promising, let me call it market, because it has also commercial objective, Space Rider, is all what is linked with biology and pharmacological application. Because of the fact that you can achieve and obtain compounds that simply cannot be done on Earth, it opens opportunities. If you are able to discover a new kind of molecule that is not able to be reproduced on Earth, then it could be a breakthrough for pharmacological application, for example. But, and here we have the link with Earth observation and the specific context of this forum, it is a platform. It is a platform for technology demonstration and validation. Mariano first said a very clever thing. Imagine that you have an instrument. The cost of an instrument is in the order of hundreds of millions of euros, or in the case of a big telescope, it can be in the range of billions of euros, and you need to prove your technology. There is a famous mantra at NASA that is test as you fly as you test. What does it mean? If you test something, you should fly what you tested, because you tested it and you are sure that it works. Or fly as you test, or test as you fly. If you want to fly something, you should try to be as much as possible representative of what will be the environment that this instrument will experience during its life. And what's better than having a space vehicle that is rounding around Earth at a low Earth orbit in microgravity condition, exposed to radiation, these exactly the very same conditions in which this experiment will fly. So you can reproduce a small technology validator for a new technology, and then fly on board on a Space Rider, and the capability to re-enter from Earth and land on the ground and make possible a direct physical exploitation of the experiments can be a real added value with such kind of application. And we can go on the next slide. And the next slide is funny because it's the mission profile. So it's a very, let's say, realistic representation of what will be the Space Rider mission. So we will launch from a space center in Guyana, thanks to a Vega-C launcher. We will be on board on the top of the fairing, so the upper part of the launcher. We will embark payloads inside the cargo bay of the Space Rider. And then this is a realistic representation of what is a usual Vega-C launch. You have the separation of stages, and then last part with the opening of the fairing, then the vehicle is exposed to the environment, and then the final separation. With respect to a standard satellite that has to stay in orbit for years, we will stay in orbit for a few months, and having this possibility to have direct exposure to space environment and microgravity simulation, we will be able to perform different set and kind of experiments in orbit. We can do also, of course, Earth monitoring from space, even if for a limited time, but for specific application could be ideal because of its versatility and its capability then to re-enter. And one important aspect of a Space Rider, as I was saying before, is reusable. But to be reusable, it has to have the capability to re-enter from orbit. So once expired its period in orbit, we will do what is called a de-orbit maneuver. Then there will be the separation and the re-entry from the atmosphere. That is the most challenging phase of the flight. Very harsh environment, more than 2,000 degrees that has to be withstood by the thermal protection on below. And then we will open this parafoil that is a steerable parachute, and we will land on ground precisely, meaning precisely, when I say precisely, I mean 150 meters of precision. That is already pretty remarkable. And then this very important capability to have the possibility for the customers to take back their experiments and really physically exploit it and understand what actually happened on space. And this is the mission profile of the Space Rider. Inaugural launch is placed in 2028, within mid-2028, and we will land in Santa Maria of Azor. That, I tell you, it's a very nice place to land on, because it's a very nice island. And to conclude this presentation, and I speak on personally and on behalf of Mariano, and in order to understand and protect Earth, we need to increase our autonomous and independent capability to access to space, but not also to access to space, also to operate and innovate in space. And this will be instrumental also for the future of Earth observation and understanding of climate changes and what is happening on our Mother Earth. And with this, I conclude our presentation. And I open the floor for question and answer, if I well understood.
I do. Q&A.
Yeah.
Not long.
Q&A for
Stay.
all.
Yeah, for everybody. So it's time for question if you have questions. We'll start with Ada.
Thank you so much for the presentation. What is the timeline for the Space Rider? And also, how you mentioned 2 months on space. Mm-hmm. And then what orbit are we talking about? You know, low Earth orbit, but how many miles above Earth?
So, timeline. In fact, the mission profile of Space Rider is pretty complex, because we have first to assemble the vehicle, then to ship it to Kourou, Then there is the integration of the customers, the payloads inside the Space Rider. This normally takes 3 to 4 weeks. It depends on the number of customers, etc. It's the classical preparation in the PCU, Ensemblement de Préparation Charge Utile, was mentioned before by Mariano. Is the place in which satellites are put on board of the launcher. In our case, we have a kind of Matryoshka concept. So we put the experiments inside the Space Rider, and then the Space Rider inside the fairing of the launcher. Then there is the standard launch campaign of Vega that lasts 30 days, Vega-C, more or less 30 days. And then you have the launch. Launch is 50 minutes, 52 minutes. Our orbit is at, when I say low Earth orbit, originally it was foreseen to have it at between 300 and 400 kilometers. In order to optimize the fact that we are landing at Santa Maria of Azor, we could be eventually and probably refine this orbit and up to 500 kilometers, but this is the range, from 300 to 500 kilometers. It is an inclined orbit because we need to land in Santa Maria of Azor. It's at 36 degrees of latitude, so we need to be launched exactly in that latitude. The vehicle has a cross-range capability, but change orbital plane is very expensive from the propellant point of view, so we can change of 1.5 degree, so we can be launched from 35.6 to 37.5, but if we want to land at Santa Maria of Azor at 36 degree of latitude. And then once back on Earth, we exploit the experiments, and we need to refurbish it. So we need to make inspection, we need to see if everything is okay from the reusability point of view. Of course, we have also expendable parts, for example, the parachutes and the panels that are ejected when the parachute it opens has to be replaced. And this turnaround is as a requirement of 6 months. So to be able, within 6 months, eventually to be relaunched, depending, of course, on the customer, if the customers are interested.
Thank you for your presentation. Very interesting. My name is Paul Gross. I'm from Detroit. I'm very intrigued by the landing. It's by parachute, but it's a horizontal landing. I don't see any wings for stabilization, and it just seems like a sudden, unexpected gust of wind could be traumatic for this. I mean, have you already tested the landing? Is this something you're all very confident about now?
Yeah, this is, of course, first of all, you're right. The fact that we are subjected to wind and we have to land against the direction of the wind, for example, induced as a first outcome that our landing zone is circular. So it's not a classic landing strip because wind can come from any direction. So we need to be able to land at that, in that direction in which the wind will be there. And we struggled, of course, on this, and we came out with a very nice solution, that is the use of meteor drones. So we will use meteor drones. These meteor drones will be launched from 0 to 2,500 meters of altitude. They will measure the wind constantly, and they will feed the vehicle in order that the algorithms for guidance, navigation, and control will be fed with actual wind, actual with a delay of a few minutes. And of course, we will have to rely also to local precise meteor forecast in order to avoid days in which there is, for example, also heavy rain or in which heavy winds are forecasted. For this reason, we also establish a very precise set of check to be performed before authorizing the re-entry. Because once you authorize the re-entry, within a couple of hours, we will be there. And so within 2 hours from the commanding the re-entry of the vehicle, we have to be reassured of the readiness of the landing site, of all the facilities, but also and mostly from the meteor condition point of view. But this is something similar that happens with less stringent requirements also for a launcher. When you have a launch, you have always a balloon, so sondage at high altitude that have to give you the green light in terms of, for example, strong wind at high altitudes. And the very last check is 10 minutes before, no? 10 minutes before the launch, for example, you have the very last checkpoint for monitoring, which is the meteor condition. The idea is to land, not the idea. The requirement is to land in Santa Maria of Azore. The idea and objective is to land there in the summer because it's nicer. But anyway, you know the anticyclone of Azore better than me. These months between May and September are very stable from the direction of the wind. They are very stable, not so strong wind, very few precipitation, very few possibility of rain, and this is our target. So for this reason, we're saying mid-28 is our target. Then we always reason in terms of statistical probability. So in 1 year, we have more or less 60-65% of probability to have a green light, but this 65% is not equally distributed over the year. In between May and September, we are more in the range of 80-85%. If we go to December, we go towards the 20-30%. So this is a constraint. It was different in French Guiana because we have more rain but very more stable wind. It's always 5 meters per second coming from north or west. So French Guiana in this sense is very reliable.
I have one question, and it's going to be the last question. I'm very sorry. There's something I'm trying to understand. At the beginning, they showed us that you were able to do atmosphere 3D images. To do that, it's a geostationary satellite that does that?
No.
It's a polar satellite?
Yeah, but
It's a special orbit, which is called the SSO.
sun-synchronous.
Sun-synchronous orbit. Most of the satellites for Earth observation use this orbit, which is nearly polar. And in this orbit, the characteristic of this orbit is that the satellite has the same inclination with respect to the sun. And this means that when it passes, it goes like this, and the Earth rotates. So when the Earth rotates, you illuminate the same point with the same angular, with the same illumination of the sun. And this allows you to have the same photograph each 2 weeks.
And then normally we have 2 satellites that are 180 degrees. So all the sentinels, for example, the concept is to have 2 satellites that goes in this way while the Earth rotates. And on the polar, you pass there many times per day because you have 17 orbits per day, okay? And so the capability to have the very same observation is multiple per days. When you are close to equator, because of the rotation of the Earth, the more you go far from the pole and close to the equator, this capability to pass again on the same place reduces up to 2 weeks with 1 satellite. With 2 satellites, it's less than 1 week, 6 days. In 6 days, you have a full coverage of the Earth, and in the very remote place on the equator, at least after 6 days, you will pass again with a satellite, with one of the 2 satellites, again in the same point with the same sun illumination.
It is crucial also for crisis management, as Simonetta said. Because for crisis management, you want to see what are the damage, if there are areas in which you have to arrive, and so on. So it's crucial that you have the same picture, because otherwise you can misunderstand what you're seeing.
And it doesn't matter that the atmosphere on the pole is much thinner than the atmosphere on the equator, who's much thicker.
No, you have to think about the fact that visible instruments are just a small part of this kind of satellites. All what is done is not done in the visible, so you can pass through the clouds, you can pass through whatever you want, depending on the length that you use in terms of electromagnetic wave. So synthetic array radar, for example, goes in the infrared, but you can go in the ultraviolet. Depending on which kind of parameter out of the 27 you want to monitor, or use a dedicated instrument that normally most of them, apart if you are really interested in the visible range of frequency, get rid of whatever is in between.
Thank you very much, Lou.
Thank you.